Welcome, everyone. My name is Carlo Campajola, and I will be talking about this work on the Scoredriven Kinetic Ising Model, which is a way of modeling time-varying interactions in complex systems. This is a joint work with Domenico Di Gangi, Fabrizio Lillo, and Daniele Tantari from Scuola Normale Superiore and the University of Bologna. So the key ideas behind this work are that we want to generalize the kinetic Ising model to have dynamic parameters, and we want to do so using an optimal and resilient technique. And the reason to do so is that we want to overcome any systematic errors that may arise due to misspecification when you fit the model on a time series. We want to be able to anticipate the forecasting accuracy in practical applications, and we want to be able also to separate different contributions to the dynamics, in particular whether there are endogenous or more exogenous contributions to the dynamics that you observe in your variables. So just a quick refresher on the kinetic Ising model itself. The model has n spins, as is usual, binary spins that interact through a matrix, have local fields H, and the distribution, the probability distribution for the configurations is given by the usual Boltzmann distribution, except for the fact that here there is time. So there is a dynamics from the configurations at time t to the configurations at time t+1, mediated by the J matrix and the local fields for each individual spin. And you can easily write the log likelihood for this model, and the partition function is easily computable. What about score-driven models then? They are a particular class of observation-driven models where the time-varying parameter, which you can call f, for instance, has a given dynamics, which is agnostic towards the real dynamics that generated the data. And in particular, the dynamics has the form of an autoregressive process where you have a dependency on past values of your time-varying parameters f, and a score-driven part of the dynamics, which depends on the gradient of the log likelihood at previous points in time. What does this mean? It means that at any point in time, when you update the value of your score-driven parameter, the dynamics will follow the likelihood in its steepest ascent direction. So basically, you incorporate the new observation that you find by shifting the parameter, the value of the parameter, towards the maximum of the likelihood. And in this modeling approach, the time-varying parameters are actually deterministic functions of the observation. There is no noise in this formula. So you don't need Markov chain Monte Carlo to actually compute the likelihood of the model and then optimize the values of the parameters. Moreover, you are able to recover any sort of dynamics, because even if you don't know the actual rule of motion for your time-varying parameter f, it will be your observation model that drives you towards the optimal value of the time-varying parameter, and you don't need to actually assume anything more than a mild autoregression on your time-varying parameter f. So in particular, you see this if you try to play a bit with these kind of models, that if you simulate a deterministic parameter like this one, which is a sinusoid in the black line, and you try to filter it using this sort of modeling approach, well, you easily see that the dynamics is recovered pretty well. So how does this apply to the kinetic Ising model in particular? Well, the first thing that we do is we let the noise be time varying. So we give dynamics, score-driven dynamics, to the beta parameter. And in particular to the logarithm of beta, because we want beta to be positive, because it doesn't make sense to have a negative value of beta. And of course, the interpretation of this is that since at higher beta, you will have a lower entropy of the model, then the sampling would be less unpredictable. But then can you also do better forecasting when beta is higher? Are your forecasts more reliable? Are they more accurate? Well, the answer is actually yes. So here I am showing you the theoretical values of the area under the rock curve at different values of beta using this kinetic Ising model. And you see that this is a growing function, as you should expect. But the cool point here is that this actually reflects also on data. Once you are able to fit this score-driven kinetic Ising model on real data, I'm not showing here for the sake of time, but we did it on financial application, you're able to have better forecast at higher beta. And so beta tells you how much should you rely on the kinetic Ising model to do your forecasts at any point in time, and can be useful in practical applications. Another kind of kinetic Ising model, a score-driven kinetic Ising model that we propose, is the dynamic endogeneity kinetic Ising model. And here the question is more like what determines the outcome of the dynamics? What determines the observation? Is it endogenous interactions, or is it exogenous sources of dynamics of influence? Well, we try to answer this question by introducing 4 different time-varying parameters. One will be modulating the intensity of self-interaction, so we'll be modulating on the diagonal of J. Another one will be modulating the intensity of interactions, so the off-diagonal elements of J. And then there will be one that modulates the intensity of the local fields, beta H, which multiplies Hi, and another one, which is a homogeneous external field, which affects all spins at in the same way, and might be a proxy for any sort of external stimulus that you have to the system. Okay, what is the classical application of this sort of model? Well, the kinetic Ising model itself has been used in several iterations with neuron data, and in particular with spike data. So basically, we have in this data set that is publicly available, we have 40 salamander retina neurons, and that are exposed to a light stimulus over a period of 20 seconds in a time binning of 20 milliseconds. And there is a +1 in the data if the neuron is spiked in the last 20 milliseconds. Otherwise, it's registered as a -1. And usually, if you would like to have a time-varying kinetic Ising model, a time-varying parameters kinetic Ising model for this sort of system, you should need more than one replication of the experiment in order to be able to average the value of the time-varying parameter over all the replicas and be able to give dynamics to your parameters. Our advantage in this sense is that we don't need multiple replications of the experiment. In this case, the data comprises 297 replications of the experiment, but we can fit a different value of the time-varying parameters beta diagonal of H and H0 for each of the replicas and compare them later. And this is exactly what we did. So here you see the values of the off-diagonal beta, of the H beta, and the H0, so the external field, which represents the external stimulus. And the solid line that you see is the mean of the realizations across 297 different samples, whereas the area is the confidence bands at the 90% level, which means that 90% of the replicas are within those bands. But still, what you see is that there is both a variability within the sample, which is given by the dynamics of the light stimulus, which varies its effect on the neurons itself. But also there is a variability across different samples, which is represented by this shaded area, which tells you that these different samples are not entirely equivalent, basically. So having an inference method which does not rely on multiple experiments to calculate your time-varying parameters kind of evades from this drawback. Okay, how good is the dynamic endogeneity kinetic Ising model at actually representing the dynamics of the data? We take 2 higher order statistics here. One on the left is the distribution of the number of synchronous spikes over the time series. And you see that the data in black show a specific distribution. And if you only fit a kinetic Ising model without time-varying parameters, this fails completely at replicating this sort of statistics, whereas the dynamic endogeneity kinetic Ising model, just adding 3 for time-varying parameters, is able to simulate much closer to the data that we have. On the right side, you see a similar statistic, which is the rank plot of the zip plot of the data, and it's well known that when you have a driven system, the frequency with which patterns present themselves within the data is inversely proportional to the rank. And you see that the data in black follows the zip flow pretty nicely, whereas if you take the static KIM without time-varying parameters, it fails at reproducing this distribution for the most frequent configurations, whereas the dynamic endogeneity kinetic Ising model is way more accurate in the replication of the statistic. So in conclusion, we introduced the Scoredriven modeling for a well-known spin system, and in particular, the dynamical noise kinetic Ising model gives dynamic insight over forecasting accuracy, which is useful in many applications. The dynamic endogeneity one highlights the relative importance of different components of the dynamics. And as I was saying, there is a very big advantage over standard methods, which is that we don't need multiple runs to compute these parameters. And there is a vast range of applicability, of course, because as is shown, we have applications in neuroscience, but we also presented some applications in finance and in temporal networks, which you can find on the preprint, which is available on arXiv. And there will be a new version coming soon. For any questions and comments, I will be available at the poster session in room 4 on the June 24th. And I'm eager to hear your questions and comments, so please reach out to me. Thank you very much for your time, and have a good day.